In this video, we're going to learn about the effects that IMFs have on the physical properties of different molecular compounds. So in general, strong IMFs correlate with a compound having very low vapor pressure, a high boiling point, high surface tension, and high viscosity. And we're going to go into why right now. So with vapor pressure, we can say that strong IMFs result in a compound resisting evaporation. And so, for example, water has a very low vapor pressure at any particular temperature. And the reason for it is that there's just strong attraction among water molecules. If I have a water molecule here and here, the hydrogen of one is attracted to the oxygen of another. We know that there's hydrogen bonding that's going on here. And just in general, you won't have a whole lot of this separation going on unless it gets quite warm. On the other hand, if we look at the left here, we have gasoline, and you may have noticed if you've ever pumped gas, if a drop of gasoline spills and hits the ground, you'll smell it immediately. That's because gasoline evaporates quite quickly. And it might make sense to you because if you look at this molecule, this molecule octane is the vast majority of gas, and it is a very nonpolar molecule. So as a result, the IMFs are rather weak. There are only dispersion forces holding them together, and they evaporate pretty readily. And that's why octane, this chemical, has a pretty high vapor pressure versus water has a low vapor pressure because the molecules stick together. Similarly, we can talk about boiling point. Well, a chemical with strong IMFs will resist evaporation in the same way that we were talking about before. If I've got water, I really need to make the molecules move quite fast, meaning get the temperature high to make it so that they become free of each other. Otherwise, they're very strongly attracted and it's just hard to separate them. And if we look at this chart, we can actually see some interesting comparisons. Now, I can compare H2O with H2S because they are similar. Oxygen and sulfur are both in group 6, but the reason why water evaporates, or rather boils, at a higher temperature than H2S is that there is hydrogen bonding among water molecules, whereas among H2S, there is not hydrogen bonding. There's London dispersion forces, of course, just as in both cases, but H2S has dipole-dipole interactions that aren't quite as strong as that hydrogen bonding in water. Similarly, HF is held together pretty well by hydrogen bonding. HCl, well, Cl is below F on the periodic table, so these are comparable compounds, but HCl only has the dispersion forces and dipole-dipole interactions, whereas HF has dispersion forces and hydrogen bonding. And finally, NH3 versus PH3, well, PH3 has the dipole-dipole interactions, but NH3 has the hydrogen bonding. Interestingly enough, when we get down here, we go to from group 6 and 7 and 5, and this is a group 4 element, carbon, that we're comparing with another group 4 element, silicon. We know that the carbon-hydrogen bond is not polar enough to result in there being hydrogen bonds among CH4 molecules, and that's why it has a very low boiling point. This is a nonpolar molecule. There are only dispersion forces, and SiH4 also only has dispersion forces, but because it's bigger with a larger electron cloud, it will have a higher boiling point. All right, so moving on to surface tension. The explanation here is that strong IMFs among surface molecules will support the weight of something that is standing on the surface of water, for example, a water skimmer. And I'm actually going to bring in this model right here. Let's just say that this is the surface of water. Granted, the molecules will be moving around a little bit, but let's just say that they're all stuck here at this exact moment that something tries to step on that water. So I'm going to put my finger in here to try to, and you know what? I can't really break through. I'm trying to push through, but there's such strong attraction among these molecules that it's hard to really pierce through. If there weren't so strong of an attractive force, then you just go straight through. But because there's strong attraction among these surface molecules, we can say that there's strong surface tension. And that's why, for example, the water skimmer is able to walk on water. If it were placed onto something else like, I don't know, acetone, which is nail polish remover, weaker IMFs, it would probably sink straight through. All right, next, viscosity. This is the final property that we'll look at. Molasses, what else? Honey, lots of syrupy substances. They resist flow. They are very viscous. And they do this because they have strong IMFs. When you think of all these syrupy substances, they have a lot of sugars in them. And those sugars, here's an example of sucrose. Sugar has a ton of hydrogen bonding among its molecules, and you can probably see why. Look how many OHs there are. There's an OH here, 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 here. They're all over the place. So an adjacent sucrose molecule will have tons and tons of interactions with the O's and H's here and here and here and here. And so that's why sugar molecules will stick together very well. And in syrupy substances like actual syrup and honey and molasses, you have high viscosity. Anyway, that is all for this video on effects of intermolecular forces. Hope it's been helpful. Feel free to leave any questions or comments in the comments section below. Thanks for watching.